So we're going to start on the gas laws, which is the next section of Phys Chem. Originally, people thought that there were four states of matter: earth, air, fire, and water. And these ones lasted for quite some time, but the modern idea is more that our earth is related to solid, water is liquid, gas is air. So what's fire? Fire is a peculiar substance called a plasma, which is very much like a gas, except that it's ionized particles. We're not going to talk much about plasmas, in fact, none. We're just going to concentrate on the solid, liquid and gas, which is what you started with in Year 11. So with a bit of a revision, let's look at the properties of each of those states. The motion of the particles is the kinetics. So we looked at kinetics before when we were looking at reactions. This time we're looking at the kinetics of gases. So in a solid, particles can rotate and vibrate around fixed positions, but in a liquid they have a little bit more movement, which is called translational motion, and in a gas they have a lot of translational motion. To change state from a solid to a liquid or to a gas, it all happens by increasing the temperature. So your temperature really relates to how fast molecules are going and how much motion they have. The properties can be defined again in this table. So you're looking at things like the density or the shape, the movement. So in a solid, they only have vibrational. In a liquid, they have vibrational and a little bit of translational. And in a gas, it's rapid, random translational motion. And that leads us into the kinetic molecular theory of gases. So there's about four postulates in this theory. Basically, the first one is that gases are hard, spherical objects in a state of continuous random motion. So the analogy most people have is billiard balls. You have a whole bunch of balls that are just wandering around, and they move in a straight line until they collide with another particle or another billiard ball or with the walls of the container or the edges of the billiard table. They are much smaller than the distance between the particles. So the billiard ball table is much bigger than a billiard ball, and when they collide, we assume that they collide elastically, which means that there's no energy loss, which means that they'll move off with a similar velocity or a similar momentum. What is interesting is that the kinetic molecular theory doesn't take into account a couple of things. It assumes that there's no attraction between particles, and that when they collide, there's no energy lost. So what that means is that there's no attraction between particles, so they never actually form molecules. They never actually interact with each other. There's no repulsion as well as no attraction. And things like gas reactions, where you require two gases to actually form together, collide, interact, and then move off as either a molecule or as different particles, those things are not covered in the kinetic molecular theory of gases. A couple more things. The pressure of the gas is due to the collision of these particles with the walls, and the average kinetic energy of a gas particles depends just on the temperature of that gas, nothing else. And we can define that distribution of energies through the Maxwell-Boltzmann distribution. And this looks at the number of molecules or the number of particles and their speed. So most of the particles have an average speed, and that average speed is defined by their temperature. So at 0 degrees, they're mostly around here, but there's some a little bit smaller, some a bit faster. Then as you increase the temperature, you can see that the distribution gets bigger and bigger, and your temperature increases and increases. So as the temperature increases, the average speed increases. As you can see, there's the average speed increasing, but the number of molecules with that speed decreases. The total number of molecules in the distribution is constant, and you can always see that some molecules have smaller speeds and some have faster, which is a great way of describing how molecules interact. Pressure is due to the collisions of the particles against the walls of the container. In a physics term, we might talk about the total force that is exerted by the gas in terms of the force per unit area of the wall. And this is important because that is actually what the units of pressure are, force per unit area. We have a couple of other ways of describing it, but that's the measure. Atmospheric pressure is the measure of the total force per unit area of a surface that is exposed to atmosphere. And the atmospheric pressure is not constant because it depends on things like the height above sea level and the weather conditions. some of the ways that they've started to measure pressure. And originally it was measured by Andreas Torricelli in 1643, an Italian. And he looked at the measure of pressure in terms of millimeters mercury. So he's looking at this length or this height of mercury in a tube. And he found that 760 millimeters mercury is equivalent to 1 atmospheric pressure. It's also called a torr after Torricelli. 1 atmosphere is 760 millimeters mercury, also called 760 torr. But the SI unit, so the standard unit for pressure, is actually newtons per meter squared, which comes back to that force per unit area, which is also sometimes measured in kilopascals. Other common units are atmospheres, bar or millibar, pounds per square inch, which is PSI, which you might find when you're pumping up your tyres of the car, those sorts of things. How would you measure the pressure of the gas? Well, there's an instrument called a manometer, which measures gas pressure. And it's a similar sort of setup to the barometer, except for the fact that you're measuring a height as relative to atmospheric pressure. So if your height is smaller here than atmospheric pressure, then your gas has a lower pressure. Whereas if your height is larger, your gas has a higher pressure. And you can look at the gas here, go pressure of the gas is the pressure of the atmosphere plus the height. So that's, or pressure of the atmosphere minus the height. And that gives you those descriptions. So here are some of the common pressure units. Pascals, kilopascals, which is just 1,000 pascals. Here, you just convert that to kilopascals just by dividing by 1,000. 1 atmosphere. It's nice and simple. 1 millimeters mercury, which is that torr that we're talking about, 760 millimeters, and bar. So these are all the pressures at 1 atmosphere, so at normal pressure. What happens if we want to convert? So, for example, at the top of Mount Everest, the pressure drops. How much is that? Well, it's easy to work out what the pascals is. You just times it by 1,000. What about an atmosphere? Atmosphere, what you do is you say, okay, well, x over 1 equals 30 over 101. So 30 over 101 will give you about 0.3. That seems about reasonable. Same sort of thing. So this over that gives you that over that. This is just simple ratios. And that gives you 225. And you can check and go, okay, it's got to be less. Yeah, it's about a third, no problem. And this one, again, if it's 0.3 here, it's around about 0.3 here, just accounting for the 101.3. Same thing happens down here. We can do the same sort of thing and look at a quarter of an atmosphere, which is basically when you go up in an aeroplane, that's where you're going. So again, divide by those ratios and you get similar sort of numbers. What about in the Australian synchrotron? Now this is a very, very low pressure. We're talking ultra high vacuum. So normally we work in pressures of about 10 to the minus 13 bar. So in terms of torr or millimeters of mercury, that's about 7 by 10 to the minus 11. What does that work out in atmospheres? That's about 10 by 10 to the minus 10. Okay, so 9 by 10 to the minus 11 atmospheres. And you're trying to think of that in terms of millionths and billionths. That's about a billionth of an atmosphere. It's very small. That's basically what you might get in outer space. Again, in terms of kilopascals, 1 by 10 to the minus 11, and just times that by 1,000, 10 to the minus 8. What about if you're underwater? You know, the pressure increases. So let's have a look. 200, so about 200 times the amount of kilopascals there. So times that by 1,000, 2 by 10 to the 5. What about atmospheres? Well, that's about 200 times here, so that's about 2 times, yeah, 1.97. Again, we can work it out. I'll let you work out for 50 meters underwater and see what you get. There are several laws that we look at for gases. One of the laws is called Boyle's law, which looks at the pressure of a gas, which varies inversely with its volume. And you can go and have a look at a simulation here, which will let you have a look at later. If you look at the volume on pressure, this is actually Boyle's results. And his experiment gives you a description that looks like that. So you can see that the pressure versus the volume is an inverse relationship. So cool. If you look at the 1 over V and plot that, you can get a relationship that looks like that. So looking at pressure versus 1 over volume, you get a linear relationship. This was from 1662, and he basically stated as, for a given quantity of gas at a constant temperature, the volume is inversely proportional to the gas. And he gave it as a constant. So P times V is equal to constant, which is where you get your linear relationship. And this is correct for pressures close to atmospheric, but at very high pressures or at very low pressures, this law doesn't work. Why? Well, that's because the kinetic molecular theory actually says that as the molecules get closer together, there must be more interactions, and the volume of the gas itself must be considered. So kinetic molecular theory stated that the volume of the particle itself was insignificant when compared to the volume of the chamber. But when you have very, very high pressures or very, very small volumes, those postulates of kinetic molecular theory start to break down because you actually start to get interactions. Charles' law. This one is related to the volume and the temperature. So for a fixed quantity of gas at constant pressure, the volume increases linearly with temperature. And you can look at the temperature down here in terms of degrees Celsius, and you can look at how that works. And this is for any gas at various pressures. There is a linear relationship. What happens? Well, kinetic molecular theory, again, faster molecules at higher temperatures need more space. So if you're looking at constant pressure, then the volume increases linearly with temperature. So there's also another website that you can go and have a look at. The description of that temperature graph gives you an idea. If you look at this graph here at 0 degrees, it all passes through here, but all of these graphs have a trend and they all end up at the same point. And if you extrapolate all of these gases to a volume of 0, you get a temperature of minus 273. And this was defined as the Kelvin scale, or minus 273 is defined as absolute 0. Reason why they put it like that is because of the way that you write the gas laws. If you put it in terms of centigrade, then suddenly you start doing things like dividing by 0. Not so good. So if you use it in terms of Kelvin, then you're always adding 273 to your values, and you never divide by 0. So Charles' law is then rewritten as V is equal to a constant times T, where T is in Kelvin. Just out of interest, the lowest absolute temperature that we've got in the lab is 10 to the minus 6 Kelvin, so very, very close to absolute 0. But the background temperature of the universe is about 2.7 Kelvin, so even higher than that. So you can go and have a look at this simulation if you want, and I'll leave you to go and have a look at it, just so that you get an idea of how these gas properties work. Make sure you keep the gravity and the type of the gas and the container constant.